Thank you, Tima, and thank you to everyone for taking the time to join us today. Native Instruments' story actually began in 1994. Founder Stefan Schmidt, a hardware engineer and musician, felt restricted by the size, expense, and sonic limitations of the physical instruments available to him. Seeing the ever-growing power of computers, Stefan realized that this could be harnessed to create highly flexible musical instruments. And he developed a modular software synthesizer together with fellow founder programmer Volker Hintz, and this would become Generator. Generator led to the founding of Native Instruments, which has remained true to and continued to build upon Stefan's vision ever since. Native today has an extensive portfolio of synthesizers, sample-based instruments and effects, plus the authoring platforms KONTAKT and REAKTOR. And these are most recently presented in Komplete 13, which we released at the beginning of October. Now, whilst the computer offers immense power and flexibility, the benefits of hardware instruments, particularly the physicality, tactile qualities, the immediacy, the muscle memory, were missed by music producers and composers, and this led to a boom in the controller space. Native Instruments' first entry into this space in 2004 focused on creating a dedicated hardware controller for a specific software application, in this case, guitar rig. And if you fast forward to 2009, this approach is further refined with Machina, our music production and performance instrument. Machina is again powered by a dedicated software application, but in this case, it's designed from the ground up to be operated as a hardware instrument first. In 2014, the Komplete Control keyboards took the exact same concept to Komplete Instruments, and in 2015, this was extended to our partners with Native Control Standard, a topic that we've talked about at previous audio developer conferences. Now, fast forward to the present, and there is another key benefit of hardware that many music producers increasingly crave: the creative, distraction-free zone away from the computer. And this brings us to the next chapter in Native's evolution: standalone hardware. Our story has always been about augmentation and not about replacement. So the question here is, how do we augment everything that is great about software instruments and effects, and everything that is great about dedicated controllers for those, and create a musical instrument that can provide a creative space away from the computer? And where should we begin this journey? Looking at our portfolio and the music production landscape, we decided that Machina was a natural fit for this. In case you are not familiar with Machina, you can see here one of the dedicated hardware controllers, the Machina Mark III. This is connected to a computer running the aforementioned dedicated software application, which is also called Machina. And it can be opened as a standalone application or as a VST, AU, or AAX plugin. And this brings me to our challenge. Could we make Machina truly standalone without losing the benefits of the existing controller plus computer system? And to talk about this, I pass you over to one of the lead engineers on the project, Vincenzo.
Thank you, Tim. So you have just seen a picture of our Machina Mark III controller. And one important aspect of it is that it was already designed with the idea that most of the functionality could be accessed without even looking at the computer screen. And that made it a great candidate for our first steps into the standalone devices territory. When we kicked off the project a few years ago, the goal was to create a product that would work as a fully standalone device, but could still be used as a controller when connected to a computer. That's how we started our journey into the embedded domain. And in the next minutes, I'll walk you through the key aspects and the major challenges that we faced during the development. So we wanted to achieve a level of performance comparable to what our users are used to on their laptop or desktop computers. And we wanted it to be as much as possible compatible with our existing ecosystem of products and services. That means sound packs, the so-called expansions, but also all the virtual instruments and effects our company is very well known for. Last but not least, we didn't want to build a one-off product, but rather a tech stack that could serve as the foundation of our future hardware products. So let's look a bit at the requirements. First of all, we wanted to build a product that would have the same set of features of the desktop version rather than just a light version of it. When it comes to I/O and connectivity, it was clear that besides audio and media I/O, we needed some kind of network interface like Wi-Fi so that the device could talk to our existing server-side infrastructure for downloading products and updates or activating products and so on and so forth. And what else? Some kind of user storage. So an SD card reader seemed to be the logical choice. USB connectivity, both as a device and as a host, so that users could connect and use existing peripherals like MIDI controllers or even external audio interfaces. On top of that, there were, of course, mechanical and thermal constraints, since the device needed to be portable. And in fact, we wanted it to have the very same form factor of the existing MASCHINE Mark III controller. And we wanted it to be passively cooled, since, well, musicians are quite sensitive to noise sources. We wanted the device to be as secure as possible. I mean, after all, you don't want your next embedded product to be mining Bitcoins for some evil hacker. So we wanted to reduce as much as possible the potential attack surface. So now that we went through some of the requirements, let's have a look at the main ingredients to build such a product. Well, first of all, we needed to choose an operating system. And the first option was not to use any. That's the so-called bare metal approach. This can lead to a very efficient use of the hardware, so it could make a lot of sense for products with a very limited set of features like simple guitar pedals or Eurorack modules. But the product that we had in mind was way too complex to be designed without an operating system layer. Not to mention that the whole system design would become way too coupled to a specific hardware platform. So the next option would have been a real-time operating system, something like FreeRTOS or VxWorks or the likes. Now, they have a very deterministic behavior when it comes to scheduling tasks, which is a crucial aspect in a system that should deal with low latency audio. However, they are not designed for complex multi-threaded applications, and well, they require quite some effort when it comes to adapting existing desktop code or even properly writing device drivers. The third option was to simply use a general purpose operating system, something like Windows or Linux. And as a company with a strong focus on desktop software, this option seemed quite appealing to us, especially when looking at the in-house expertise. One of the other main ingredients of such a system is the application. And we had the option to either rewrite it from scratch for this product or to adapt the existing code base so that it could run on the operating system and the hardware that we would eventually choose. We decided to adapt our code base. And one of the nice implications is that any update to the desktop version could easily be available on the standalone version as well. And last but not least, we had to choose the underlying hardware that would run the operating system and the application. And in this domain, the main question that we had to answer was whether we wanted to use an ARM or an x86 CPU. So now let's focus on the operating system and see how we ended up choosing one. At this point, we still didn't make any decision regarding the hardware. So we needed an operating system that could ideally support both ARM and x86 architectures. A crucial aspect is definitely the level of customization that the operating system allows, so that we could optimize the boot time and define the exact set of services and applications that would run on the device. The level of maturity is, of course, something very important, as well as how well the operating system is maintained and supported. Another crucial aspect for an operating system that should deal with low latency audio is the real-time capability. it's quite clear that we are not designing a device that has hard real-time requirements, but we still need the system to be as deterministic as possible. So we need at least a soft real-time capable operating system. Now, we don't have the time to dive into details here, but there have been a few talks in the past edition of ADC, which went quite deep into this topic, so I definitely encourage you to watch them. Anyways, back to our OS decision. A few more important aspects are the availability of device drivers for existing chipsets and peripherals, support for various file system types, both for internal usage and for the users, built-in support for various hardware protocols, because, well, you don't want to be reinventing the wheel all the time. And last but not least, the development costs involved, and most importantly, the pricing model. With all of that in mind, it was quite clear that Linux was the way to go. In fact, Linux is widely adopted in many industrial domains. It's free, it's stable, it's mature and well maintained by a huge community of developers. It has a lot of configuration and customization options, but unfortunately, it's per se not a real-time operating system. So what are the options then? Well, you can add real-time capabilities and transform the Linux kernel into a fully preemptible one by using the so-called preempt RT patch. This is a set of changes that nowadays is about to make it into the mainline kernel, and it's very easy to configure and use. On top of that, you can further improve the system behavior by using techniques like CPU core isolation or by explicitly setting the CPU core affinity and so on and so forth. A more radical approach would be to use a hypervisor-based solution, something like Xenomai or Jailhouse. Well, such solutions allow for extremely low and deterministic scheduling latencies, but they come at the price of a higher complexity when it comes to the initial setup of the system and so on. So they tend to be generally more coupled to a specific hardware. Again, we don't have time to dive into technical details, but there's a very well-written set of articles on the ELK audio blog that I can definitely recommend if you want to dive deeper. So at this point, we decided to use Linux, and in particular, to use the preempt RT patch. So how could we get to an operating system image? Well, building a custom Linux image can be very time-consuming. Especially if you need to support different underlying hardware platforms and CPU architectures. Luckily, there are several open source toolchains available, like YOCTO or Buildroot or OpenWRT, just to name some of the most popular ones. In this scenario, YOCTO is the de facto industry standard. So let's look at it in more detail. First of all, YOCTO is well maintained. It's modular by design, and it's very scalable. It is very well supported by the majority of the hardware vendors, and it works with many different hardware platforms, thanks to the so-called board support packages that you typically get from the vendors themselves. When using YOCTO, you can build the operating system image, but also the development SDK and all the tools that are needed to build and test code that will then run on the specific OS image. Now let's focus on another very important component of our embedded system, and that's the main application. So when working on the main application, one of the main challenges was, of course, to port the internal libraries and the application code itself to Linux. Some of the libraries that our application relies upon are developed by third-party companies, so we had to get in touch with them and get the Linux-specific binaries. But besides porting the code, the main challenge for us was the creation of a headless flavor of our main application and plugins. Because we're not running an X server on the device or any kind of desktop environment. So basically, we had to separate the main desktop GUI from the display rendering, which is still required on the embedded version as well because of the two high-resolution color displays. And last but not least, a lot of effort went both on the engineering and on the sound design side to optimize everything for a smaller and less capable CPU. And speaking of it, one of the most important parts of an embedded product is the CPU. And the main decision we had to make was, first of all, the architecture. There are many silicon vendors currently offering ARM system on chips with multiple cores, both in symmetric and asymmetric configurations. And with ARM system on chips, you typically get more onboard peripherals. And in general, they tend to be more power efficient. One of the downsides is that many ARM system on chips tend to have a very short life cycle, as they are targeted to devices like smartphones and tablets, which normally have let's say, a very scoped market life. x86 CPUs, on the other hand, are produced by only 2 silicon vendors, but they tend to be available on the market for a longer time frame, especially the versions that are targeted at industrial applications. Another important aspect is that code written for desktop is likely to run better on the x86 architecture. Now, with the introduction of the Apple M1 system on chip, things may look a bit different in a few years from now, because many companies will have to port their code base to ARM anyways. But that's another story. So, which is the right CPU or system on chip for our product? Here's some of the criteria that we use to decide. First of all, mainline kernel support. Otherwise, you might be stuck to specific kernel versions and bound to the support that you get from the vendor, which sometimes can be rather limited. What else? The so-called SIMD-ness of the code. That is how your code base, especially the DSP code, deals with vectorized code. If you're lucky, you are already using something like Boost SIMD or XSIMD, which will take care of mapping the specific intrinsics to whatever is available on the underlying hardware. For instance, Neon on ARM or SSC or any of the other recent extensions on x86. If you're using vendor-specific libraries like NE10 or Altivec or Intel's IPP, or even worse, if you decided to write hand-rolled SIMD code, well, it might be a bit more complicated to switch from x86 to ARM and vice versa. So ultimately, the final decision was taken after looking at the benchmarks that we've been running on the different hardware platforms. And of course, at other less technical but still fundamental aspects like the pricing and the long-term availability of the silicon. For all these reasons, we ended up choosing an x86 platform, at least for our first embedded product, and more specifically an Intel Atom. So what's missing? Well, unfortunately, porting the application and running it on a customized image on the hardware that we chose was not the end of the whole development process. There are a number of features that are typically available on desktop systems that need to be implemented or at least exposed to the user via the main application's user interface. Some good examples are connecting to a Wi-Fi network or pairing to a Bluetooth device, and so on. On top of that, we had to implement a secure mechanism for deploying and installing operating system and application updates. And last but not least, an embedded system needs a few more services and tools that can improve the overall reliability and robustness of the system. For instance, watchdog services, recovery tools, and so on. Another service which has already proven to be crucial for us is centralized crash reporting, because it's very valuable. It's a very valuable way of measuring the health of each release as soon as it hits the customers. So after years of development, we now have a solid CI infrastructure that allows us to build the operating system, the SDK, the applications and the plugins, the content products, and everything that runs on the hardware. We are currently building a hardware farm and extending our testing infrastructure. More importantly, we are able to deploy updates, additional plugins and sound packs using our already existing server-side infrastructure via the so-called native API. In fact, our desktop software called Native Access, which is used to download and update products, has been transformed into a service that runs on the device and is used by the main application to perform any product-related operation. More importantly, we reached feature parity with the desktop version of Machine, and the embedded version is now just a plain build flavor. This allows us to release features both on the desktop and the embedded devices at the same time. And of course, this has a great impact on the maintenance effort and the overall quality of our software. There are, of course, many other aspects and details that we didn't have the time to even touch upon, but I hope this gave you a good picture of the efforts and the challenges that are involved when transforming a desktop application into a fully standalone device. And since we're talking about results, I'd like to hand it over to Tim, who will tell us a bit more about what all of the process I just described means for our customers. Thanks for your attention.
Thank you, Vincenzo. So thanks to the work of every department across NI, we shipped Machine Plus on the 1st of October 2020, and we've been thrilled to see such a great reception so far from the community, the press, and first customers. Today, Machine Plus is running the full versions of Massive, Monarch, Prism, FM8, Retro Machines Mark II, KONTAKT and REAKTOR factory selections powered by the full KONTAKT and REAKTOR engines, Phasis and Realm, as well as Machine's internal drum synths, bass synth, and internal effects. Additionally, it's compatible with 70 plus existing expansions and will be compatible with all upcoming expansions. As a platform, it will continue to grow with new features and more content. So Machine Plus represents an evolution of Stefan's original vision. It's a physically small device with vast sonic capabilities that is now combined with all of those benefits of a standalone hardware instrument. The physicality, the tactile qualities, the immediacy, the muscle memory, plus the creative distraction-free zone away from the computer. And we're really excited to hear the music that people are going to create with it. Now, before closing, one final note. If you'd like to be part of Native's product creation team and work on some of the products that we have talked about today, we recently opened a number of C++ and other positions. So if you're interested in applying for any of these or learning more about them, please visit native-instruments.com/career-center, and that's center ER, or speak to myself, Vincenzo, or one of our colleagues in the virtual conference room, or of course on Discord. So lastly, thank you very much for joining today, for taking the time. Thanks to ADC and the organizers of ADC for all of their work in what has been a very, very difficult year for a lot of us, I'm sure. And I hope that you enjoy the rest of the conference. Thanks very much.